Hey guys, Ms. Peterson here, and welcome to AP Chemistry Lecture 7-1, all about dynamic equilibrium. This will be our introductory lecture to really get a conceptual understanding of what equilibrium is, how it's reached, how we describe it, and how to write equilibrium expressions. So let's get started. So far in this class, we've only been talking about reactions that go in one direction, reactions where reactants turn into products. But that is just not the case in real life. In real life, many chemical reactions are reversible, meaning that just as the reactants form products, the products can turn into reactants. So we have to use different methods when describing those systems. And when they are done reacting, okay, I say that in quotes because they never quite stop, we call that dynamic equilibrium, okay? And go ahead, just take a nice big breath for me. Did you feel that oxygen being absorbed into your blood? Okay, and it travels to your cells and then that oxygen is then released? That's a reversible reaction. Oxygen binding and being released from the hemoglobin molecules in your red blood cells. You can think about the water cycle, how the water evaporates and then it turns into clouds and then condenses and falls as precipitation. You can think of the exchange of hydrogen ions in acid-base reactions or electrons in redox reactions. Okay, they go in both directions. All examples of reversible reactions where we need descriptions of equilibrium in order to describe them. So, what is equilibrium? Okay. For a system to be considered at equilibrium, there need to be 3 conditions met. Also, I do want to point out that all of our equilibriums are dynamic equilibriums. So there's really no distinction between dynamic equilibrium and equilibrium. I will use those terms interchangeably. So for equilibrium to be reached, 3 conditions have to be met. You need to have some reactants and some products. Even if they're in very small amounts, it can still be considered at equilibrium. Then what's going to happen is the forward and reverse rates of reaction, so reactants turning into products and products turning into reactants, are going to happen at the same rate. So just as many reactants are turning into products as there are products turning into reactants. And when you have 2 processes occurring at the same rate, what happens? Well, there's no overall change. Because if just as many A is turning into B as B is turning into A, on the macro level, you're not going to see a change. Okay, the concentrations remain constant. Okay, let me reiterate that. The concentrations remain constant. The reaction rates are equal. Okay, a very common misconception is thinking that equilibrium means equal concentrations of the things, and that is just not true. In fact, equal concentrations very rarely occurred. Very, very rarely occur. Typically, the equilibrium is going to favor either the reactants or the products, and you're going to have more of one than the other. Okay. In a graphical representation, we can see it here. This is probably the most famous reversible reaction, the synthesis of ammonia. We'll talk about why it's so important later in this unit. But we can see in a graph of the concentration versus time that the concentrations level out. They do not equal. Okay. We can see here that at equilibrium, there's still more hydrogen, more nitrogen than there is ammonia. Okay, so this is an example of a reaction that favors the reactants because there is simply more of them at equilibrium. Okay, now for the graph that you will also see is a graph of reaction rate. Okay, and there we see that the rates end up being equal. Okay, so this point here and this point here are the same point, the point at which equilibrium is reached, and there is no more net change in the concentrations of reactants and products. Why don't those erase? There we go. Okay. Now, I want to also use this to explain something else. Okay. Say we start with just reactants. Yep, we have low concentration of that. We're starting with just reactants. Initially, that reaction is going to go pretty fast. But as the ammonia, as that product's being produced, its concentration is going to increase. Now, remember back to kinetics. What happens when concentration increases? The rate of the reaction increases. So as the concentration of reactants decreases, okay, that's going to increase the concentration of the products and thus increase the rate of the reverse reaction. While as the concentration of reactants decrease, that is going to decrease the rate of the forward reaction. And it's that balance of the reaction rates speeding up and slowing down as those concentrations change. They really determine where equilibrium lies, okay? Is it reactant favored or product favored? Now, that's called the position of equilibrium, okay? And you'll hear it two ways. Often we will say that the equilibrium lies to the right. Okay, if we have a reaction written, reactants. Oh, this is the dynamic equilibrium arrow for reversible reactions. So anytime you see that arrow, know that we have a reversible reaction and an equilibrium system. Okay, now if equilibrium lies to the right, that means it favors the products. Okay, this is an example of a reaction in which the equilibrium favors the products, okay? Because we can see there are more products than reactants at equilibrium. But if equilibrium lies to the left, the reactants are on the left. It favors reactants. This is an example of a graph of concentration. This is concentration as well, that favors the reactants. Okay, now the position of equilibrium depends on a lot of different things. It depends on the concentrations, it depends on the energies, it depends on the organization. There are a lot of different factors, and we'll get more into those later in the unit. Okay, cool. Okay, cool. So now when we talk about equilibrium, okay, we use equilibrium expressions, okay? And basically, an equilibrium expression is used to quantify the equilibrium, okay? We use a constant, K, that is temperature dependent. So there are different K values depending on what temperature the reaction is going to be completed at. However, the equilibrium doesn't change with regards to initial concentrations or initial pressures, okay? Though those things can affect the position of the equilibrium, it does not affect the equilibrium constant, okay? And once we get further into the unit, you'll see a little bit about what that means. But there are some things that we definitely know. If K is greater than 1, that means that the reaction favors the products, okay? Then if it's less than 1, it favors the reactants. You will not see negative K. There's never going to be a negative K value. It will always be a positive number, okay? Because K, what it really is a ratio. How we write them is based on the stoichiometry of the reaction, okay? So say we have this reaction, A, molecules of A, react with B, molecules of B, in a reversible reaction to form C, molecules of C, and D to D. The coefficients become exponents. Coefficients become exponents. And in general, we have the products over the reactants. So with it being a ratio, hopefully you guys can see that if K is greater than 1, that means the number on top, the products, are bigger, where if K is less than 1, it favors the reactants. Now, what's also important to note about this, sometimes K is going to be much, much, much greater than 1, okay? So if K is much, much, much greater than 1, okay, that really means it really strongly favors the products, aka it's a one-way reaction, okay? Reaction goes, I'm going to go ahead and say almost to completion, meaning there's going to be very little amount of reactants at that equilibrium. Where if K is much, much less than 1, that means things stay mostly as reactants. They don't really form into products, okay? That means reaction barely happens, okay? It just barely happens. Maybe it happens a little bit, but there's not going to be too much there, okay? Now, there are a ton of different notations for the equilibrium expressions. They always follow the same formula of products on top, reactants on bottom. They're raised to the power of their coefficient. Also, important thing to note, pure solids and liquids, like a solid, are not included because their concentrations wouldn't really make sense. How do you say the concentration of water in my cup of water here? How do you talk about the concentration of salt in a spoonful of salt? It just doesn't quite make sense. It's not something they do. Really, we say their concentrations are about 1, and we just do not include them in the equilibrium expression, okay? Their concentrations will be pretty constant. We only include the aqueous and the gaseous species, okay? Now, just to get you oriented to all of the ones that we'll use, okay? This unit, we're going to be focusing mostly on Kc, which are equilibrium expressions using the concentrations, Kp, which are equilibrium expressions based on the partial pressures, and Ksp, which we use when ionic compounds dissolve. Okay, this chunk is what we're going to be mostly doing this unit. Where this chunk, the acid, base, and water dissociation constants, okay, those are equilibrium expressions for those. We will hit those really strongly in our next unit, which is dedicated to acids and bases. Okay, and note, though these are all different subscripts, they're all different versions of KEQ for the equilibrium constant, or sometimes you'll see it as just K. Okay, so it's all going to be pretty similar. What I don't want you guys to get confused about is this is capital K for equilibrium constant, not the lowercase k, which we used in kinetics. Okay, this is always going to be a capital K. So really, I think we just need to see it. Let's go ahead and write the Kc and the Kp for the following reaction. So first, we'll do the concentrations. Remember, when we're doing concentrations, we need to use the square brackets, okay? Square brackets mean concentration. And it's going to be our products, which are our NO2, the molarity of the NO2 raised to the 4th power, times H2O, which they say is a gas, so it does get included. If it was a liquid, it would not get included, raised to the 6th power, over the concentration of the reactants. NH3 has a coefficient of 4, so it's raised to the 4th power, and O2 raised to the 7th power. Easy enough, right? Okay, now for the pressure one, okay, these are all gases, so they're all going to get included. But for pressures, we really want to use not square brackets, okay? Square brackets are only for molarity, so we use the curved brackets. And we actually, instead of saying the formula, it's the pressure of NO2 to the 4th power times the pressure of H2O to the 6th power over the partial pressure of NH3 raised to the 4th power and the partial pressure of O2 to the 7th power. Okay, cool. So let's look at a couple other ones. We have the Haber process, like I said, the most famous of chemical reactions. In this chemical reaction, nitrogen gas reacts with hydrogen gas, our equilibrium arrow, to form ammonia gas. And then, of course, we need to balance it before we can accurately write the equilibrium expression. There we go. It's balanced. Now, this one, we could either do a Kc with the molar concentrations or a Kp with the partial pressures. I'm just going to go ahead and do the Kc. So we have the concentration of N2, no coefficient or a coefficient of 1, so no exponent, aka exponent of 1, times the concentration of H2 to the third over the concentration of NH3 squared. Also, just to point out, on the top, it doesn't matter if you have N2 times H2 to the third, or if you were to switch it and have H2 to the third times N2, it doesn't matter. 2 times 4 is the same as 4 times 2. So those orders don't matter. Okay, cool. Okay, cool. Now we have one, solid calcium fluoride dissolves in water. Okay, this is something dissolving. It's actually going to be a KSP reaction. Now let's go ahead and write, what does dissolving look like? Dissolving looks like we have a solid. Okay, so calcium is 2 plus, fluorine is 1 minus, so calcium fluoride is CaF2, and it says it's a solid, and then it's going to dissolve into calcium ions and 2 fluoride ions. Okay, and if they're dissolved in water, you are aqueous. Now, remember back when we learned about solubility rules, and I just told you some things don't dissolve? That was a lie, okay? Insoluble salts or soluble salts do dissolve, and we can quantify how much they dissolve using the K values. Our insoluble salts are going to have Ks that are very, very small, on the order of 10 to the negative 3, 10 to the negative 4, where things that readily dissolve, like table salt or sodium chloride, have very, very high KSPs, okay? Now note, solids don't get included in the equilibrium expression, so we're not going to have a denominator here, and that's totally fine. We do not need a denominator in our expression. It's fine to just have it be the ion times the ion. Okay, cool. Okay, cool. One more. We're going to do ammonia, a base. Oh, base, that means we're going to be doing Kb. And it reacts with water in an acid-base reaction. So we need to write that reaction. Ammonia is NH3, okay? And it's reacting with water. Now, water, we normally do not say aqueous for water. Water is a liquid. It is a pure liquid. Because it's present in such high amounts, its concentration doesn't really change when it reacts. So we have ammonia reacting with water. Ammonia is a base, which is a proton acceptor. So it's going to form the ion NH4 plus when it accepts that base from the hydrogen ion from the water, and it'll leave that OH minus there. Okay, so when we write the expression, it'll be the products. So NH4 plus, nope, it's already balanced. We're good to go. Times OH minus over the H2O liquid does not get included because its concentration is constant. So just over that NH3. Okay, cool. Okay, cool. Last thing I want to show you guys is modeling systems at equilibrium using particulate diagrams. Okay, how you might see these on the AP exam. So here is a question where we have a mixture representing NO2 and N2O4 in a 1 liter container at a given temperature. And the two gases have reached equilibrium according to the equation below. We have the equation. Based on this particular diagram, is the equilibrium constant greater than, less than, or equal to 1 at this temperature? Justify your answer. Okay, so for this, we do need to understand what the equilibrium expression would be. It would be the concentration of N2O4 over the concentration of NO2 squared, okay, because we got that 2 there. And there's a couple different ways we can figure out if this is going to be greater than or less than or equal to 1. First, we could just count the particles. Note, in this, we have 1, 2, 3, 4, 6 NO2s and 2 N2O4s. Oh, sorry, 3. I can count. Okay, and 3 N2O4s. So we got 3 of these and 6 of these. We have more NO2. Okay, so does that mean that the equilibrium lies with the reactants to the left or with the products to the right? Okay, well, we have more reactants. So the equilibrium lies with the reactants. Okay, it is reactant favored, which means that K will be less than 1. Okay, we could have also said hypothetically that, say, the NO2, each of these particles represents 1 mole. So then we could have actually calculated a hypothetical value, and we would have 6 or 3 over 6 squared. 6 squared would be 12, which is 1/4, which we do know is less than 1. Okay, cool. Okay, cool. Okay, let's go down to this one. Hydrofluoric acid is an acid with a Ka of 6.8 times 10 to the negative 4. Note, K is less than 1, so that means it favors the reactant. Which of the following best represents the ionization of hydrofluoric acid in water? They give us some of the reactant or some of the particles involved. So the reaction is we have HF giving up its proton or reacting with water. Let's go ahead and do it with water since we have that H3O plus there. So we have HF reacting with H2O to produce H3O plus and F minus. Okay, that's the reaction that we're working with here. It's an acid-base one where it's an acid, it's a proton donor, so it donates a proton to the water. Okay, now in figure 1, notice we have only a little bit of the products, where in this one we have all products, no more HF. So which one of those best represents this reaction at equilibrium? Well, figure 1. Because, okay, the reaction favors the reactants, which in this case are HF. So the concentration of HF at equilibrium should be much greater than the concentration of F minus or the concentration of H3O plus. This would be if it was a one-way reaction, all of the reactants turned into products. Okay, cool. Okay, cool. Last one. Here we have 3 reaction systems for a reaction of 2AB. Okay, A is represented by blue circles, B is represented by purple ovals. They show the changing over time. Which one took the longest to reach equilibrium, and how do we know? Okay, let's go ahead and look at these individually. Now, if we look at the reaction system 1, hopefully you notice that we have, at T2, we have 4 of our B particles, and then at T3, we have 4 of our B particles. That means that equilibrium has been reached because there's no more change in concentration. So right here, I'm going to use a star, meaning equilibrium reached. Okay, where for reaction system 2, we don't know if it's reached equilibrium yet because there's no 2 frames that show that constant concentration. So we don't know if that one's reached equilibrium yet. It might be at T3, but without another time after, we don't know. Where this one, we can see it reached the equilibrium system at between time 1 and time 2, similar to that first one, even though the